All right, everybody, this is Unit 1 tutorial on dimensional analysis and significant figures. So hopefully this will make some sense as to the application of significant figures, while also letting us work on dimensional analysis and some more complex unit conversions. So here we go. Just a review with significant figures. These are all the digits that we have to report to assess the precision of the measurement. Okay, and so for example, I think we used this one. If I measured like the length of my office, I would say that, right? How many of those digits are significant? Well, all of them, because they're non-zeros. So they're all important to this measurement. So I would say there's 4 significant figures here, right? Zeros get a little bit trickier, but the trick to figuring them out is to put numbers in scientific notation. And if the zeros go away, they're simply placeholder zeros and they are not considered significant. For example, if I have 2,500, we'll say grams of something, right? So I'm looking at this, I know that the 2 and the 5 are significant because they're not zeros. Now the question is, do these zeros count? So they have to be there. Like I have to write the zeros because I have to show the magnitude of this number. I can't just write 25 because that's not the number. The number is 2,500, right? So the question then is, do the zeros reflect the precision of the measurement? And the answer here is no, right? Because if I put this number in scientific notation, those zeros go away. Okay. And so that will be the way to tell. Okay. So we're going to kind of practice that in context as we're going. So why does this matter? Well, we need to understand that when we are measuring things, we need to reflect our precision in those measurements. So if we're going to then work with those numbers, like whether do math or things like that, we have to compound that error in our measurement to our answer, okay? And so we're going to use significant figures to help us round our answers after we do math in the class. There are a few exceptions to significant figures, and we call those exact numbers. And in other words, they're numbers that have infinite significant figures. Okay, infinite, meaning they have so many that we can't even count them. And so they're usually not our limiting factor. We always need to round our answer to the number that has the least precision, right? So if it has infinite precision, then they don't matter. So here's an example. Examples of exact values would be like counting of objects, right? So like, for example, there are 12 eggs in a dozen. That's an exact value. It's not 12.0 or 12.00 to show my precision. Like I know it's 12 and it's exactly 12 and it's to the infinite amount of significant figures, right? How many people are in a room and so on and so on. So counting objects is a good example. Another good example would be from a defined quantity. In other words, it's in the definition of the substance. So this would be like 100 centimeters is a meter. That's an exact value. That's literally the definition of a centimeter, is that it's 100th of a meter. And that's just a fact, right? There are 12 inches in a foot. That is the definition of the measurement, okay? Now, me saying that there are 2.54 centimeters in 1 inch, that's different. That's a measured value because that's not the definition of a centimeter. I'm now having to convert a unit from the American system to the international system, the metric system, and those are not based off of each other. So that's the difference, okay, between exact values and measured values, okay? Let's see. The only other one would be like if it's a number part of an equation. So like, for example, there's the radius of something is defined as the diameter divided by 2. So this 2, I'm not factoring in, like that's an exact value, right? Like that it's literally the diameter divided by the whole number 2, okay? But for the most part, we're talking about counting objects or defined quantities, okay? So how do we do this? Okay. If we are adding or subtracting, and again, all these notes are posted on PowerSchool, by the way. So if we're adding and subtracting numbers, the rule is you round to the number of decimal places as your least precise measurement. Doesn't matter how precise you measure one side or one measurement, if your other is incredibly imprecise, then it doesn't matter, right? It kind of negates it. So here's an example. Let's say we do this plus that plus that, okay? So do the math first, right? Just do the basic math. Add these things together, right? And then we're going to write down exactly what either your brain or your calculator tells you, okay? Which in this case is this, okay? So if we were in math class, that'd be your answer and we'd be done. Problem is we're not in math class. So we need to round our final answer to the number of decimal places as our least precise measurement, right? So we have 2 decimal places here, 3 here, and 1 here. So we must round our answer to 1 decimal place. So I'm going to cut off my number here. And then to decide if I round up or down, I look immediately to the right of that. I see it's a 0, so I'm going to round down. So I'm going to say the answer to this problem in science class is 13.0. That is the most precision that we can give given the measurements that we have here. It might very well be 13.001, but we don't know that, and we don't have enough evidence to support that. So the most certainty we can give is 13.0, which basically says it's somewhere between 12.9 and 13.1, right? That's our error range, right? So that's when you're adding and subtracting. When we are multiplying or dividing, right? Multiply or divide. The rule is very similar, just one little tiny difference, okay? We're going to round the answer to the number of significant figures, not decimal places, of the least precise measurement. Okay? So we're going to round it to the sig figs this time. The reason why it's different, okay? The reason why it's different is because with multiplication and division, that's going to compound our error in a different way than just adding and subtracting. And so we have to then show that in our math. So let's take those same numbers we just had, but let's multiply them instead. Okay. So again, I'm just going to punch these into the calculator. And I'm going to write down exactly what my calculator tells me, which is that. So now we have to decide, okay, where do we cut this off? So I'm going to count significant figures in each of the numbers I have here. Okay. So 7.5, I have 1, 2. So that has 2. 1.001, these count, and then these zeros count because they're in the middle. So that actually has 4. And then this one has 3. This 0 counts because it's after a significant digit, after the decimal. So least precise measurement, 2 sig figs, which means I can only report this answer to here. So how am I going to round? I'm going to look immediately to the right of that 3. I'm going to say it's a 7, which means I'm going to round up, which means I'm going to say the answer to this problem is 34. That's it. That's the most precise that I can say with confidence the answer to this problem is. Even though your calculator will give you all these digits, doesn't matter. You have to cut it off. Okay, so that's going to be how we do this. So now what we're going to do is we're going to try a problem, and you guys are then going to try and round your answer to the proper sig fig. So we're going to kind of rope in dimensional analysis and sig figs here with some practice problems. Okay, so let's calculate these things out. So I'm going to put one in here. Let's take one from your textbook, actually. Let's do that. So let me insert questions directly from your textbook. Let's see. Let's do that one. No, not that one. Try one more. Sorry about that. I don't know where it went, but that's okay. Anyway, we're going to do this one too. So we'll do this one first. This one was actually one of the ones you had for homework. So we're going to do this one. And we're going to go through it carefully. So a flask containing 11.7 milliliters of a liquid weighs 132 grams with the liquid in the flask and 124.1 when it's empty. So how are we going to calculate the density of this liquid to the correct number of sig figs? So remembering a couple of things: density, mass over volume, right? And then we also need to solve for our mass because they give you the liquid in the flask or in the graduate cylinder or flask and the actual weight of the flask. So we have to do some math first. So to get the mass, it's going to be 132.8 grams minus 124.1 grams to get my mass. Okay, so we're going to do this math. And then we're going to round our answer appropriately. So this is going to give us an answer of 8.7 grams. So now I have to report this to the proper sig figs. So we're subtracting. So we need to go off of decimal places. This has one decimal place. This has one decimal place. I'm going to report my answer to one decimal place, which in this case is just 8.7. So we're good here. If I needed to report a second decimal place, just hypothetically, but the calculator only says 8.7, then you need to add a zero. You need to say 8.70 in order to actually represent your significant digits. So there's our mass. So now we're going to say density equals mass over volume. So again, I'm just going to do the math first. And we're going to get that big long thing, gram per milliliter. So now we divided. So now we're not going to go off decimal places. We're going to go off of total significant figures of our weakest measurement. So that's going to be the 8.7. So I can only report my answer to two significant figures, not decimal places, significant figures. Okay. The zero here doesn't count. So I'm going to say 7 and then 4. And then I'm going to look immediately to the right and see it's a 3. So I'm going to round down. So I'm going to say the density here is that. And that is the level of precision that we can give. Okay. Okay, let's try a trickier one. I'm going to write this one. I'm going to wait on the ibuprofen one. Okay, here we go. Actually, no, we'll just do this one. You have a similar one like this for homework. There's a lot going on in this problem. Okay, here we go. Ibuprofen, which is a painkiller, if you're unaware. It's a class of painkillers called NSAIDs, or non-steroidal anti-inflammatories. They're really good for like if you get like a sports injury or something like that, because they reduce inflammation. Okay. So we want to be careful when we're giving drugs like this to babies because we want to get the dosage right, because it's based off of your body weight, not of anything else. Okay. So here it is. There's a suspension for infants that has this in it. 100 milligrams in 5.0 milliliters of suspension. Okay, that's the drug we're given. The recommended dosage for babies is 10 milligrams per kilogram of body weight. How many milliliters of this suspension should be given to an infant weighing 18 pounds? And here it says, assume two significant figures. So that means we're going off of the 18 pounds likely here, okay? So sometimes when you have some tricky measurements, they might help you and tell you some sig figs, but we'll go through and make sure anyway. So what information do we need to know? Well, I think we need to know pounds to kilograms, right? So I'm going to give you that is about that. I'll go 3 sig figs on that one. So we'll say that. So we have that conversion, and then we've got to figure out the rest of this thing. So here's what I'd recommend. I'd recommend you pause the video for a second, give this a shot on your own, try to set it up as dimensional analysis in fractions in one calculation. The fewer calculations we can do, the better our sig figs are going to be reflective of our measurement, okay? And so it'd really be to your advantage to try and do this in one step, okay? So pause it, try it on your own, and then come back for the answer. Okay, so here's the way I thought about this. I have a fractionated unit here, right? 100 milligrams per 5 milliliters. I have a fractionated unit here, 10 milligrams per kilogram body weight. So for me, those make sense to use as fractions in dimensional analysis. So which number should I choose to start with of my 3 here? I'm going to choose the 18 pounds because I think that's going to be the easiest to work with. So I'm going to start with 18 pounds. And then I'm going to turn that into kilograms of body weight. Now I'm writing body weight in here because we have grams of body weight, but we also have grams of the drug. And I want to make sure we're being careful about which one we have. So I'm going to say that in 1 pound, there's that many kilograms of body weight. So now I'm in kilograms of body weight. So what could I turn that into? Well, if I come up here, I have this. So I can say that in 1 kilogram of body weight, there's 10 milligrams of the drug. So now I'm in milligrams of the drug. And I know that up here, in 100 milligrams of the drug are in 5.0 milliliters of the suspension. So now, if I did this right, I should be in milliliters. So let's just double check. Pounds cross out. Kilograms of body weight cross out. Milligrams of the drug cross out. And I'm left with just milliliters on the top. Okay? So this should be set up right. Now, if I just do this math, we do 18 times 0.454 times 10 times 5 divided by 100. My calculator says this. So we're only half the battle here. Now we have to decide at what point to cut this off. Where am I going to round this? So I need to look at all my numbers and my fractions and decide what's my least precise measurement, right? What are exact values that are going to have like no impact here? And it really comes down to, and you got to think about this, okay? Which numbers here were actually measured and which are like suggestions innately in the measurement itself. So for example, the 18 pounds of the baby, right? That's definitely measured, right? You had to weigh the child, okay? This one here, kilograms to pounds. That's a measured ratio, right? It's not like a kilogram is defined as this many pounds. That's not what it is. I'm actually converting from one unit to the other. So I'm going to factor that in. This fraction here though, okay, the recommended dose is 10 milligrams per kilogram of body weight, okay? No one measured that. That's the suggestion. They're saying, roughly 10 milligrams per kilogram body weight. So no one measured that. So I would say that we're not going to factor this in Because if we were, we'd probably only use the one sig fig there. So I'm gonna say no for this one, primarily also because they told us this, assume 2 sig figs. So that probably means that we don't need to worry about this one here. This one. Now, this one is likely measured, particularly the volume, the 5.0 milliliters. That's clearly a measurement of the suspension. The 100 milligrams in it, I'm not so sure about that. You could probably argue either way for that one. So I think this is a little bit of a wild card here, but because they specifically told us 2 sig figs, I think we're going to want to just go with the 2 sig figs that they suggested. Okay. So if I want 2 sig figs, I'm going to come to here. I'm going to look immediately to the right and see that it's an 8. Okay. Don't start like all the way at the end of the number and like round. Just look immediately to the right of where you want it to go. I'm going to say 4.1 milliliters. Okay. So that's the amount of suspension of this drug solution that you'd want to give the child that would be safe, right? So what that means is you'd need to use a device that is marked at least every milliliter, right? So that way you could guess to be as close to 4.1 as possible. Okay. And so that's the least precise that we can go given the measurements of the weight that we took, which was 18 pounds. Okay. Had you more precisely weighed the child, you could more precisely give an answer there. Okay. Okay. Lots more problems for you guys to work on the homework. Okay, there's a handful more in the textbook. Give those a shot. Do your best to follow the dimensional analysis process and try and round your answers accordingly. Okay. And then you guys are good to go for the weekend. Okay. Have a great weekend, guys, and I'll see you on Tuesday.